Hello, we continue learning physical methods of investigation, and now we continue nuclear magnet resonance in our first video lesson dedicated to NMR spectroscopy. We talked about the mechanism of how nuclear magnetic resonance is carried out, and we entered into the interpretation of results. And in this video lesson, we are going to talk about what to understand and how to understand. Okay, here we go. Okay, in general, we can see different types of signals in NMR spectroscopy. They can be singlet, doublet, triplet, quartet, yeah? And if the N is the number of protons as indicated here, where N is the number of protons bonded to adjacent non-equivalent carbon atoms, and N plus 1 is the number of times a peak will be split. And this is useful to know when analyzing spectra, as it means the number of hydrogen atoms bonded to adjacent non-equivalent carbon atoms can be determined from peak splitting. If the N is 1, so then it will be singlet. When N is 0, it will be a singlet. When N is 1, it will be 1 plus 1, 2. This is 1 actually, yeah. When it is 2, N plus 1, 3. When it's 3, N plus 1 is 4. Now we are going to understand what they stand for here in this page. Okay, if we have such a compound, ethanol, okay, we can divide the hydrogen environment into 3 categories. These 3 hydrogens have the same category, these 2 hydrogens have the same category, and this hydrogen is different from all other remaining 5 hydrogens. This is understandable. So this is A category, these 2 are B category, and these 3 belong to the 3rd category. So methyl group can be named or can be classified as triplet, and as we see here, triplet. And how many hydrogen are there? Okay, here we know there are 3 hydrogens. There are 3 neighboring hydrogens. And this is the point we have to understand. N is the number of protons bonded to adjacent. Okay, this means here we if we have triplet 3, this kind of triplet signal, this means it belongs to C category. How many hydrogens are here? 3 hydrogens, yeah. And here we have quartet belonging to B category. Okay, why are there 4 here in quartet here? Because N equals here 3, which means here in B category there are 3 neighboring hydrogens. Okay, and here how many neighboring hydrogens are here in C category? In C category there are 2 neighboring hydrogen, and in B category there are 3 hydrogen atoms. So N plus 1 equals 4. N here is 3 in B category. In B category, there are 3 adjacent hydrogen atoms, neighboring hydrogen atoms. 3 plus 1, so 4 quartet. And in C category, how many neighboring hydrogens are there? 2. They belong to C category. And in C category hydrogens, there are 3 adjacent hydrogens. There are 2 adjacent hydrogens, 2 neighboring adjacent that belong to another carbon. So 2 plus 1, 3. This is what we have to understand. And why is this only 1 singlet? Because it belongs to only, let's say, 1. hydrogen that does not have neighboring, let's say, hydrogen atoms. So this is what we have to understand. This quartet belongs to these two hydrogens, which means it has three neighboring hydrogen atoms. Okay, three neighboring hydrogen atoms plus one, so they are four. And in this C category, there are here two hydrogen atoms in neighboring carbon, two plus one. So this have the same type. That's why it's one. So they are triplet. Okay, we don't have to exchange triplet and quartet by the meaning. Triplet belong to triplet belong to triplet belong to let's say 2 plus 1 category, 2 plus 1 category, 2 neighboring hydrogen plus 1, and B quartet belongs to 3 plus 1, 3 adjacent hydrogen plus 1 category. That's why it is quartet, and this is triplet. Okay, good. So methyl group shows triplet here. CH2 group shows quartet next to 3, and this is next to 2, and OH appears as a singlet, no splitting. Okay, next. Okay, and in our previous lesson, video lesson, I reminded about tetramethylsilane. And this is the structure of tetramethylsilane. They have the same category. I mean, this molecule has the same category of hydrogen. All these 12 hydrogen are linked to the carbons, to 4 different carbon atoms, and those 4 methyl groups are linked to the central silicon atom. That's why their position is the same. So they produce a single peak as indicated here. This molecule is non-reactive and volatile, and it has low chemical shift, and it does not interfere with others. That's why it's used as a reference compound. Okay, next. And deuterated solvents. We know hydrogen has only one proton, it has no neutron, and deuterium has one proton and one neutron. And for HNMR spectroscopy, samples must be dissolved in deuterated solvents because it contains only isotopes 2 hydrogen that don't have an overall spin, or solvents that have no hydrogens in, such as tetrachloromethane. So this is the point why deuterated water or deuterated chloroform is used in NMR spectroscopy. And why not just use normal solvents like normal water, protein holding water, or chloroform. Protonated solvents interfere with HNMR signal, and deuterated solvents contain only deuterium, which does not show up in hydrogen NMR. From this point of view, okay, deuterated water or deuterated other compounds can be used as solvent. And this is deuterated chloroform. It also has this kind of single peak, as I reminded. That's why it can also be used for HNMR, and the peaks resulting from the deuterium does not interfere with the hydrogen peaks. Okay. Here, there is one point that we have to pay our special attention to, that while we are using D2O, here we might have an exchange between the OH belonging to alcohols, and D2O also has its own dissociation that is observed in normal water. So we might observe the exchange between the hydrogen and deuterium. So it might cause kind of misinterpretations. So what do we have to do? DTO, deuterated water, contains H2 isotopes of hydrogen which do not appear in H NMR spectra. If a sample contains OH or NH and it dissolved in deuterated solvent, the hydrogen in the OH bond will be exchanged with deuterium atoms from the D2O because the deuterium does not show on a NMR spectra. No peak will appear for the OH or NH environment. And to confirm OH environments in a compound, we can run an NMR without D2O and then repeat with D2O as a solvent. If any peak in the spectra disappear, we know they must be OH group. So when we compare the compound without D2O, if it has this kind of peak, and when we dissolve it in D2O, if we obtain peak with disappeared peak that belongs to OH. So then we can make a conclusion that this peak belongs to OH. Okay, this kind of approaches help us to confirm the OH environments in a compound that could be identified by using samples with and without deuterated water. Okay, in carbon environment, if we categorize hydrogens into different, let's say, classes, categories, here we can see in the molecule of propane, all the six hydrogens belong to different categories. This 1, 2, 3, and 1, 2, 3 hydrogens belonging to methyl groups, edging methyl groups, are the same category. And the middle and the hydrogens located to the central carbon atom are in other categories. So there are only two hydrogen environment in this molecule. And if we compare the same molecule according to carbon environment, here we can see 5 different carbon environments. The total number of carbon here is 6, 1, 2, 3, 4, 5, 6, but these 6 carbons belong to 5 different carbon environments. This methyl group and this methyl group both are linked to the carbon that is linked to another carbon and that holds one hydrogen. So these two methyl groups are categorized as the same class. Okay, and this is another category, and this one is another category because it is linked with oxygen, and this is another category because it's linked with oxygen and with another oxygen as carbonyl group, and this one even if has a kind of methyl group, it is different from these methyl groups because these methyl groups are linked to the carbon, which is linked to another carbon. And here we see that this methyl group is linked to the carbon that holds a carbonyl group. Okay, that's the part of carbonyl group actually. Okay, so this compound has 5 carbon environments, and this compound, the same compound, has 4 different carbon environments. These 6 hydrogens belong to the same type of category as we see, because both belong to the methyl group that's linked to another carbon group, and this is another hydrogen environment, and these 2 hydrogens belong to another hydrogen environment, and these 3 hydrogens belong to another hydrogen environment because these 3 differ from this and these 3 hydrogens with the linkage that this methyl group was linked to another carbon, which is a part of carbonyl group. Okay, next, if we have this kind of structure, normal propanol or propan 1-ol, propanol 1, whatever. Okay, so we might obtain this kind of carbon signals, that were obtained in carbon 13 NMR. So They are three. Why they are three? Because in this compound there are three carbon environments: methyl group, methylene group, and methylene holding OH group. So it has this kind of signals. Okay. And now we are going to see some examples of proton nuclear magnetic resonance spectrums. If we have this kind of structure, carbon 6, hydrogen 12, and oxygen 2, and we have one singlet here, doublet here, and multiplet here, and doublet here. So what do you have to do? Here, as we see, number of carbons 2, and here 3, and here 6, and this is one multiplet. How do we have to explain these results? Again, this is singlet, adjacent protons, and this is doublet, one adjacent proton. Okay, singlet belongs to the hydrogen, which is linked to a carbon that has no a carbon that has no carbon linked to that carbon, or that has no hydrogen as a part of the adjacent carbon. We talked about that. Okay, doublet means that it has one adjacent proton, triplet has two adjacent protons, and quartet has three adjacent protons, and multiplet has 4 plus adjacent protons. Again, let me remind you not to be confused, this structure. Again, please. Singlet belongs to this one because it belongs to a hydrogen that has no adjacent hydrogen. And triplet belongs to two hydrogen or hydrogens that has two adjacent carbons. Here, triplet, this triplet has two adjacent carbons next to methylene group. And this quartet belongs to methylene group that has three adjacent hydrogens. Okay, so this one quartet belongs to CH2. This one belongs to CH2 because it has three adjacent hydrogen atoms. Okay, now we go back to our compound here. So doublet means one adjacent proton, triplet means two adjacent protons, quartet means three adjacent protons, and multiplet means four adjacent protons. Okay, and we have this kind of compound. And how do we have to interpret those results? Okay, this one, 6, it has doubled with peak intensity 6. Okay, it has doubled signal and peak intensity is 6, which means, okay, it has 6 hydrogens in this environment with one adjacent hydrogen. One adjacent hydrogen because it is doublet. And the number of hydrogens 6, and since it is doublet, it has one adjacent hydrogen. Okay, what about this? It is singlet, and it has 3 hydrogen in this functional group, so it belongs to the methyl group. And what about this? It is a doublet with a peak intensity 2. It belongs to doublet which has one adjacent hydrogen as indicated here, doublet, one adjacent, and the number of hydrogens in that group is 2 because peak intensity as indicated here is 2. Okay, and here multiplet with a peak intensity 1. Number of hydrogen is 1 here, but it belongs to multiplet, which means in the neighboring atoms, in the neighboring carbon atoms, to which belong the carbon that holds this, the hydrogen that has this peak, is considered as a multiplet. Okay, so this multiplet can be understood that it belongs to this kind of structure. Why this kind of structure? Because it belongs to one hydrogen. Yeah? Here it's indicated as one. It has only one hydrogen, and it has many multiple adjacent hydrogen atoms. How many? 4 plus. 1, 2, 3, 4, 5. Okay? 1, 2, 3, 4, 5. So as the let's say starting point, we can make a conclusion. At least it has this kind of structure, at least with 4 plus hydrogens. It can be 4 or it can be 5 hydrogen atoms in the neighboring carbons, in this and in that. Okay, so this is the peak that belongs to this hydrogen. Okay, next. And singlet with peak intensity 3, it's singlet, peak intensity 3, which means in this, okay, this peak belongs to the hydrogen, this peak belongs to the hydrogen, which has 3, the same type of hydrogens, but with no adjacent hydrogens. Why is it like that? Because it's singlet. Okay, singlet does not have any neighboring hydrogen. Okay, so the methyl group belongs to this one, and just we talked that this peak belongs to this hydrogen. Okay, next, and okay, the yellow belongs to this one, as we said, and the methyl group belongs to this one, and here we have doublet. Yeah, doublet. Doublet belongs to doublet belongs to hydrogens that have one adjacent. Okay, it has two hydrogens. It has two hydrogens, but since it is doublet, we know that in the neighboring atoms it has one hydrogen. Okay, this one hydrogen is the reason why these two hydrogens are giving doublet signal. Okay, and what about these methyl groups? How many hydrogens are there here? 6 hydrogens. And are they singlet? They are not singlet. They are doubled, right? And they have the same, let's say, they have the same category, even if they belong to different methyl groups. They can be considered to develop the same type of singlet, but they must have these all 6 hydrogens must have one adjacent hydrogen. That one adjacent hydrogen is this one. Why is this are these let's say signals doublet, and why are these signals doublet? Because this hydrogen is causing doublet signal to these two hydrogens and double signal to these 6 hydrogens. Okay, so this is one of the simple structures to develop our ability to analyze and identify the structure of compounds. Now we are going to see another good example in order to strengthen our understanding. Again, here we have a compound that has the ratio of elements carbon 6, hydrogen 10, and oxygen 2. Carbon 6, hydrogen 10, and oxygen 2. And it has one singlet, another singlet, and it has one quartet, yes, and it has one triplet. So now we are going to understand what they are. what they stand for and what they stand for. Okay, singlet. Singlet means it has no adjacent hydrogen. Okay, and since these numbers are given, we can make a conclusion. It has three hydrogens, and there is no adjacent hydrogens. So this has a methyl group. It has a methyl group, which is either linked to carbon that holds no hydrogen, or it might be linked to oxygen directly. Okay, this is the point we have to understand. And what kind of signal is it? It's also singlet. And how many hydrogens? It has two hydrogens. Yeah. Does it have adjacent hydrogens? No, it has no adjacent hydrogens. Why? Because it is singlet. Okay, so it is singlet. It has no adjacent hydrogens. And we have to understand it has to belong to the methylene group that is linked to either carbons that might not have hydrogens, or it might be linked to other atoms that holds no hydrogens. Okay, and here we have quartet, and the number of hydrogens here is 2, and it has how many adjacent hydrogens? It has 3 adjacent hydrogens. Why? Because it is quartered. It's not doubled. If it's doubled, we could make a conclusion that it has only one hydrogen, a neighboring hydrogen, adjacent hydrogen. Since it is quartered, we know already that it has 3 adjacent hydrogens. And this is triplet, and it has 3 hydrogens as indicated here. And how many neighboring hydrogens are there belonging to this peak? 2. 2 plus 1, triplet. Okay, these are the pointers that we have to think and develop our understanding. So if we, based on this kind of interpretation, explanation, if we develop our understanding, so this has 3 hydrogens, 3 hydrogens, and 3 hydrogens that belong to one methyl group, and 2 neighboring hydrogens, because it is triplet. Okay, because it is triplet. And this one, in the next page here, we can see this one belongs to the methylene group because it has 2 hydrogens here. And since it is quartered, we have to know it has 3 adjacent hydrogen atoms. So this methylene group is linked to the methyl group. And this methyl group, holding 3 hydrogens, is linked to the methylene group because it has 2 adjacent hydrogens, leading to the formation of triplet. Okay, good. Next. Here we talked about this peak and this peak, and based on this peak and this peak, we developed, it has this kind of methyl plus methylene group, ethyl group, and this one, singlet with peak intensity 2, which means it has 2 hydrogen. Since it is singlet, we have to know it has no adjacent, hydrogens. Okay, we already know it has no adjacent hydrogens. And the fourth one, we already know, singlet signal with 3 hydrogens. It has 3 hydrogens. And since it is singlet, we know it has no adjacent hydrogens. Yeah, here, that's why we have to know there is one carbon or hydrogen, there is one carbon there is one carbon or oxygen, there is one carbon or oxygen. Since we have 2 carbon and 2 hydrogen not included in this structure. So based on the signals, whether they are singlet, doublet, or triplet, we develop this kind of carbon chains. Yeah. And then we have to use our logical analysis. So by using our logical analysis, we have to develop that we did not use two carbon and two oxygen, and there is only one option. So the structure belongs to this kind of compound. Okay, I hope you understand this point is. If not, I recommend you to watch this video lesson once again. So you will be able to develop your understanding. Again, hydrogen, no coupled hydrogen. It means this is a singlet signal. Okay, one coupled hydrogen, it develops doubled. Okay, because it has one adjacent hydrogen, and triplet, this has two adjacent hydrogens. And when we have quartet, it means this hydrogen, okay, this four belongs to this hydrogen, which means this hydrogen is linked to the carbon, which is linked to another carbon that has three hydrogens, and we call those three hydrogens adjacent hydrogens. Okay, and here we can see singlet hydrogen here, and this is doubled with longer distance. Here the distance is not that far. Here the distance is far because among them there is a double bond. Yeah, and when we have this kind of two coupled hydrogens, two adjacent hydrogens, yeah, one coupled hydrogen, yeah, coupled with this one, and there are two hydrogens coupled with this one, so it develops this kind of signals, a doublet of doublet. Okay, if we have this kind of three coupled hydrogens, one coupled hydrogen, another coupled hydrogen, and another coupled hydrogen, so then we have a doublet of doublet of doublet. So as we have more complicated structure, we might obtain this kind of more and more complicated signals as well. Here we can see that 43.29 and 43.09 belongs to 5 and 4 positions, 5 and 4, 5 and 4. Yeah, and they are close to each other, but they differ from each other. That this 5 has a linkage with this carbon, with this carbon, and with this carbon. And this 4 carbon has the linkage with this carbon, yeah, and with this carbon, which has a carbonyl group, which is a part of carbonyl group, which has a double bond with oxygen. And here we can see 19.77 and 19.15. 19.77, 19.15, 9 and 7. They are also close to each other, 9 and 7. And 9 and 7, here we see 9 and 9 and 8. I'm sorry, I'm really sorry, 9 and 8. They are developing a doublet signal. This is a doublet signal, okay? Because here we can see in the third position, this carbon has a covalent bond with this carbon, with this carbon, and with this carbon, and with this carbon, it has no hydrogen. It has no hydrogen holding here. Okay, this is not a doublet structure, doublet signal. If it is a doublet signal, we had to have here at least one hydrogen this hydrogen has a linkage with all other, I mean, it has to hold one hydrogen. This carbon has the covalent bond with all the carbons. Okay, they are uh, very close to each other because both 8 and 9 belong to methyl groups. Oh, I'm sorry. This is a carbon 13 carbon 13 NMR results. Uh, I was referring to hydrogen NMR results. I'm really sorry. So they are close to each other. That's why I didn't understand this point as well. They are close to each other. They are close to each other. And that's why, okay, we see similarity between them, and they are close to each other as well. 43.9, 43.29, and 43.09. And tetramethylsilane has this kind of small signal as indicated here. Okay, so this one belongs to carbon 13 NMR results. And in carbon 13 NMR results, we can see this kind of, let's say, field for samples soluted in deuterated chloroform. The delta scale is relative to tetramethylsilane. So different functional groups might have this kind of range between, for example, 100 to 160 that belongs to aromatic compounds. Or, for example, between 100 and 190 that belongs to carbon of carboxyl groups that link to carbon. I mean, that belongs to carboxylic acids or esters or amides, is indicated here. So by checking this kind of comparisons, we can find out about the presence of different functional groups that could be identified by carbon 13 NMR results. Okay, this is the hydrogen NMR results of camphor, methyl group, A and C. They link to this carbon, and this carbon has linkage with four other neighboring carbons, and it has no hydrogen. So A and C are singlet signals, not doublet or triplet, and therefore B is also a singlet signal because it's also linked to a carbon that has the linkage with carbons only. Okay, and this is about the carbon abundance. Carbon 12 makes 98.9% of all carbon on the Earth, and 1.1% of carbon belongs to carbon 13 isotope. So carbon 13 isotope is the source that we rely to determine the structure of compounds by using NMR spectroscopy. These are all that I wanted to deliver. I express my thanks, and if you like the videos, I kindly ask you to support us with your likes, so our video lessons can reach, a wider audience. I express my thanks. Thank you. Have a good day.